So I wanted to give a little bit of a clarification, and I'm going to stand as close to the camera as I can. I wanted to give a little bit of a clarification on, actually I'm using a mic pack, so the closer I am, the louder it doesn't get any louder. I don't actually have to be this close. I just like making you uncomfortable. I'm still wearing a mask. It's one of those days. I want to give some clarifications on what I'm asking for, particularly in the following sections: power transfer and spring design. Okay. So when it comes to power transfer, this is how force is transmitted through the joints. Okay, I could have called this force transfer. You calculated forces and how the forces transfer from joint through a linkage to another joint. We're calling this power transfer because, quite frankly, what we're doing with this is calculating how much each link is giving as far as a force. And at each configuration, this is a way that you figure out how much power is transmitted. It's just linearly scaled with how much force and how fast the linkage is moving. So a force transfer, usually the force is, the force is directly correlated. You can figure out how much power is going to what component based on forces, if you know a given speed. So, with that knowledge, this is why, even though you're giving me force calculations, I'm still calling it power transfer for that reason. Because again, this is it's force if we had it moving. But instead, I'm only looking for force with no velocity. So technically you're not giving me power transfer, you're only giving me force transfer, but the concepts still carry over. Okay, so what you did to calculate forces for your component stresses, just hand me in a nice document detailing that this force, this is what you're doing for power transfer, okay? As for the spring design, there is no one right answer. Now, according to your book, you need to have a C value of D over D, which is between 4 and 11. I believe that's what the book says, this is the spring outer diameter to the wire width. Generally, if you have a C value between 4 and 11, you're in a good place. Most of the time, spring manufacturers abide by those laws, but that will be something that I'm looking for, is to make sure that you are ensuring your spring is well made, rather than buying off a knockoff spring. Okay. Now, when it comes to designing your spring, I told you earlier that it's a good idea to have a spring occur across a 1 degree of freedom joint. If you just have a spring, and you rigidly mount this to a block, and you rigidly mount this to a block, the issue is any loads coming in this direction are going to cause that spring to bend this way, and there's no control over the location. It becomes a bobblehead toy on the end of your robot leg, which is not okay. So what you need to do is you actually need to design a joint around your spring so that your joint creates a boundary condition that will take loads in multiple directions, except it will allow compression. Okay? Well, the example that I used earlier when explaining this is, imagine you have two parts, okay? This is a round bar or something that has a pin coming out of it, okay? So there's one component, and your other component is here. You just have a component that has a hole in it, and maybe this is a solid component, so this rod fits nicely in the hole. So if I move this component up, it looks like this, okay? And you have X amount of rod that comes into this component. Now, this cannot bend in this direction. If you load it this way, it creates a moment. It actually carries that moment across this joint so that no moment is transferred up here. You will have a shear force that you have to deal with, but that's about it. Okay? The goal of having this is a 2 degree of freedom system. If you made this instead of a round system, you made this a square type peg system, now this becomes a 1 degree of freedom joint where it can only go up and down. Okay, if it's round, it can also rotate and go up and down. It's okay to have a 2 degree of freedom joint for this case because if you put the spring in here, the spring is going to prevent some amount of torsion, and it doesn't hurt if there's a little bit of torsion there. Springs can handle it. But then you have your spring wrap around it like this. Okay, it creates a 2 degree of freedom joint where any non-axial loads are handled by the joint and any axial loads are handled by the spring. Okay, and that is the most robust design for this. Now, as far as what kind of parameters you put on your spring, you can have, it really depends on how much force you want this to exert at how much displacement. So let's say your robot weighs 50 pounds. Okay, if your robot weighs 50 pounds and you're putting 50 pounds of force through this spring, then your spring has to be able to handle 50 pounds. And you're designing for what compression does it have at 50 pounds. Okay, if at 50 pounds it fully collapses, you can have a problem there. Because then it can't handle any more than 50 pounds. You know, if you put something else on there and it ends up being 70 pounds, then it's bottoming it out every time, absolutely. Or if it accidentally hits something and has impact forces larger than 50 pounds, again, it bottoms it out completely and transfers that force entirely to the robot. The whole purpose of this spring is that you have some compression, but it doesn't bottom out with the weight of the robot. Now, I didn't give you a weight of the robot. You could assume 50 pounds if you really want a nice assumption value. You have to start with something. But when you design a spring, it's important you have two different factors coming in here. First of all, what is the maximum force that you expect to go through this spring? As you design your spring, you're going to have to give me that one value. I need to know that. The second thing you need to know, how much displacement are you expecting out of the spring? Okay, if vehicle shocks travel up and down like 6 inches, okay, that's kind of a lot for a robotic leg. I mean, 6 inches, your leg itself moves up and down about a 1/4 inch to 3/4 of an inch every time you sit on it. That would, if you treat your leg like a spring, that's very little. I mean, it's this much. Having that much, though, allows you to have some shock absorption. Okay, so if at 50 pounds of force causes 3/4 inch of displacement, then you have your spring constant. Your K is equal to F over D. I mean, that's it. You've now figured out your K. You know what your K is. Then it's a matter of finding a spring with the right inner diameter so that it doesn't bind around whatever you're using, something that mounts well to your system. That's it. There are a million ways that you can design a spring correctly to fit with your system. All you got to do is pick one of them. Okay? And make sure that you also have to design the joint to handle the spring. There's a huge piece of this is not just, oh, well, I picked a spring. A huge piece of this is how do you design around handling that spring? And I'm not requiring you to do a stress analysis on this. I'm more looking at how do you adjust your design to be able to handle the addition of a spring. So you will need to model this joint as a part of your spring design. You will need to figure out what your spring needs to be, and then you're going to need to figure out how to attach this. Is it just a simple staple? Are you going to weld it on? Okay. All right, that's it. Good luck on your project. Let me know if you have any additional questions. Gill out.